In this lecture, we examine the trigonometric or circular functions cosine and sine when they are defined on the complex plane. So we will explore how these two functions are related to the exponential function to hyperbolic cosine and to hyperbolic sine. We will also examine how complex conjugation affects the exponential function and the cosine and sine functions. Then, we determine the derivative of cosine and the derivative of sine when these two functions are defined for complex numbers. We will also say a few words in passing regarding the other four trigonometric functions when all these functions are defined on the complex plane. We start with Euler's formula that says that e raised to the power I times theta equals cosine theta plus I times sine theta, where theta is a real number. If z is equal to x plus I times y, where x and y are real numbers, then e to the z power equals e raised to the power x plus I times y, which equals e to the x power times e to the I times y power. By Euler's formula, e to the I times y power equals cosine y plus I times sine y, so that e to the z power equals e to the x power times the quantity cosine y plus I times sine y. The conjugate of e to the z power equals the product of the conjugate of e to the x power and the conjugate of cosine y plus I times sine y. The conjugate of e to the x power is itself, since e to the x power is a real number. And the conjugate of cosine y plus I times sine y is cosine y minus I times sine y. E raised to the power minus I times y equals cosine of minus y plus I times sine of minus y. This quantity is equal to cosine y minus I times sine y. So the conjugate of e to the z power equals e to the x power times e raised to the power minus I times y, which equals e raised to the power x minus I times y. X minus I times y is z conjugate, so that the conjugate of e to the z power equals e with z conjugate as exponent. We take e raised to the minus I times theta power, which equals cosine theta minus I times sine theta. When we add e raised to the minus I times theta power to e raised to the I times theta power, the sine terms cancel out, and we end up with twice cosine theta. Therefore, cosine theta equals the two exponentials added together all over 2. Observe that this is just the hyperbolic cosine applied to I times theta, so that cosine theta equals the hyperbolic cosine of I times theta. One can verify as an exercise that sine theta equals the quantity e raised to the I times theta power minus e raised to the minus I times theta power all over 2i, or the hyperbolic sine of I times theta over I. Extending these formulas to the complex plane by replacing theta by z, cosine z equals the hyperbolic cosine of I times z, and sine z equals the hyperbolic sine of I times z over I. To determine the conjugate of cosine z, we find the conjugate of this numerator and 2, and the conjugate of 2 is 2. By using the fact that the conjugate of e to the z power equals e raised to the power z conjugate, we take the conjugates of the exponents to find the conjugate of cosine z. The conjugate of I times z is minus I times the conjugate of z. And the conjugate of minus I times z is I times the conjugate of z. This result is the cosine of z conjugate, so that the conjugate of cosine z equals cosine of z conjugate. Using the same idea, we should be able to show that the conjugate of sine z equals sine of the conjugate of z. With the formulas for cosine and sine for complex numbers, we can now write formulas and identities for tangent, cotangent, secant, and cosecant on the complex plane. Now, let's see if the Pythagorean identity is still true. That is cosine squared z plus sine squared z still equal to 1 if z is not just a real number, but any complex number. Using these formulas for cosine z and sine z, Cosine squared z plus sine squared z equals this sum. Squaring the first fraction, we square e to the iz power to get e to the power 2 times iz. Then we have the middle term 2 times e to the iz power times e to the power minus I times z. E to the iz power and e to the minus iz power cancel out, so the middle term equals 2. Then we square e to the minus iz power to get e to the power minus 2iz. And everything is all over 4. We have exactly the same numerator for the second square, except that the middle term is minus 2. I squared equals minus 1, so the denominator is minus 4. Simplifying this difference, we end up with 2 plus 2, which we divide by 4 to get 1. So the Pythagorean identity still holds, and indeed cosine squared z plus sine squared z is equal to 1 for every complex number. Now let's verify that sine of the sum of two complex numbers satisfies the same identity for the sine of the sum of two real numbers. If a and b are real numbers, sine of a plus b equals sine of a times cosine b plus cosine a times sine b. Does this identity hold for every pair of complex numbers? Let z1 and z2 be two complex numbers. We wish to determine if sine of z1 plus z2 equals sine of z1 times cosine z2 plus cosine z1 times sine z2. Applying the formulas for cosine z and sine z to z1 and z2, sine z1 equals this fraction, cosine z2 equals this fraction, cosine z1 equals this fraction, and sine z2 equals this fraction. We factor out 1 over 4i and multiply out the numerators to get this quantity. Some terms within the brackets cancel out. And we're left with this fraction, which is what we'd get if we were to apply the formula for sine z to z1 plus z2. So the identity for the sine of the sum of two real numbers holds for the sum of two complex numbers. A similar strategy should lead to the identity that cosine of z1 plus z2 equals cosine of z1 times cosine of z2 minus sine of z1 times sine of z2. Now we check if we also get the same derivative formulas as the ones in introductory calculus for trigonometric functions, but this time on the complex plane. The product rule, the quotient rule, and the chain rule for differentiation can all be derived in ways similar to how these rules are often derived for functions of a single real variable in introductory calculus. We will not derive these rules for complex numbers, but for the rest of the lecture, we will simply assume that these rules still hold when applied to complex valued functions. Before we find the derivative of cosine z, we first show that the derivative of e to the z power is itself. Let f of z be equal to u of xy plus I times v of xy, where u and v are real valued functions. Assuming that f prime exists, f prime is equal to u sub x plus I times v sub x, where u sub x and v sub x are the partial derivatives of u and v with respect to x. F prime is also equal to v sub y minus I times u sub y. Where do these formulas come from? These are the formulas for f prime when obtained along the horizontal direction and along the vertical direction. If f prime were to exist, these two formulas should give the same value, thus leading to the Cauchy-Riemann equations. Now e to the z power equals e to the x power times cosine y plus I times e to the x power times sine y. Using this formula for f prime, we differentiate only the factor e to the x power in each term, so that we get e to the x power times cosine y plus I times e to the x power times sine y. This is just e to the z power, so that the derivative of e to the z power is itself. We differentiate this fraction to find the derivative of cosine z. The derivative of e to the iz power with the application of the chain rule is I times e raised to the power I times z. And the derivative this time of e raised to the minus iz power is minus I times e raised to the minus iz power. We multiply the numerator by I and the denominator by I times I is minus 1. And the result is minus the quantity e raised to the iz power minus e raised to the minus iz power all over 2I. This fraction is sine z. So the derivative of cosine z is minus sine z, just like that for cosine when applied to real numbers. Applying a similar strategy, one should find as an exercise that the derivative of sine z is cosine z. With the Pythagorean identity, the product rule, the quotient rule, and the chain rule for derivatives, we should be able to establish these derivative formulas, the details of which we leave as exercises.